So here we're going to do some practice problems using table I as well as thermochemical equations. Up here we have some definitions. You could always look those up. We have some questions down here. What I want to really focus on is the middle part, and that's where usually students have a lot of trouble. So just to review, if the energy terms on the right side, I highlighted them in yellow, those are going to be exothermic reactions. And so if you look, these ones in yellow all have energy added to the right side of their arrow. So it doesn't matter where the arrow is, as long as the energy term is on the right for that reaction, then it is exothermic. So these are exo. And then the rest have energy on the left side of the arrow. So these are going to be absorbing energy, and therefore endo. This part's not too hard. Next, determine the delta H. The delta H is actually pretty easy. It's the number in the reaction, okay, as long as the reaction is balanced. So for this one, we're going to say that delta H is going to equal 566.0 kilojoules. Now specifically, if you notice, I left the space. Since this reaction is losing the energy, our delta H is going to be negative. Just like if you lost money, your bank account would go negative. Well, maybe not all the time, but general idea. Your bank account the number would go down, and it could potentially go negative, and that's where this really comes from. And so the next one, it's going to be negative. It's this number with a negative sign. It's that simple. If we do the next one down, it's going to be positive, because now we're absorbing the energy. Just like if you were paid, you gain money, your bank account is going to show a larger positive number, or if it had 0, it would become positive. If it had negative, it might go positive. Point is, the number is going to go up. And so that's why positive delta H's are for endothermic, because they're absorbing or gaining the energy. So it's going to be positive 2 to 7.4 kilojoules. This one would be positive. The next one would be, so you get the idea, negative, 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 positive, positive. So I'll have you do the rest. I will send out an answer key for the rest of this. Now, heats of formation. Here's the trick. With a heat of formation, sometimes they can be the same as heat of reaction, sometimes they're different, but they are the energy needed to form the product from its starting elements. So if we look at this first one, this reaction tells us that we actually can't get a heat of formation from this reaction. Not truly, and not the way that I would teach you guys to do it. There is a way to do it, but we don't need to worry about it, because we're not forming CO2 from its individual elements C and O. We're forming it from a compound CO and extra oxygen. So this one's not going to count. So I probably shouldn't have highlighted that. I made a mistake here. I should not have highlighted that. The next one, we can do a heat of formation, because now we're forming this compound, Al2O3, from its individual elements, aluminum and oxygen. So the fact that it's O2 doesn't matter. It's still an element. So here's what it says. 2 moles of this give off this much energy. So the heat of formation for 1 mole should be half that amount. So then all we would do is just divide that number by 2, and we will get delta HF equals negative 1675.5 kilojoules. And the only difference between heat of formation and heat of reaction is just you add the F in, and that's pretty much it. The next one, we can do a heat of formation, because we're making this compound C2H2 from its individual elements C and H, right? And it says it takes 227.4 kilojoules to make, and there's an unwritten number here. You should all know it's a 1 mole of that. So it turns out the heat of formation here is the same as the heat of reaction, because we're making 1 mole. And that will always be true. If you make 1 mole of the product, your HF and your delta H are going to be the same thing. Okay, next one. Here we make 2 moles, so it's going to be half that amount, and we do make it from its elements, so we can do it on this one. So it's going to be positive there. Next one, We can't do a heat of formation on this because if you look, we're making H2O, but we're not making it from individual H and H or elemental H and elemental O. We're doing it from H and a compound OH. So you can't really do a heat of formation on that one. The same goes for this next one. We're not forming, in order to do this, we would have to form KNO3 from K and an O, KN and O, but here we're forming it from K and NO3, which does not count. So we can't do a heat of formation on that one. If you look at the next one, same reason, we're not forming, we make two products, so we would have to pick, and then it just doesn't work. So it doesn't work. You can do one for this because you're making, for the next one, because you're making HI from individual H or elemental H and elemental I, and we can do it for this one because this is what the H2O should look like for heat of formation. We're making it from individual H and individual or elemental H and elemental O. And so you can do it for these two, so I'll let you do those. Again, I will send an answer key out. You can answer the questions on the back. On the bottom, it's basically just saying how I did this. And then for the back page, all I want you to do is for these first four, I just want you to take this delta H and put it into the reaction on the correct side. So for example, since it's negative, negative means XO. All I would do is rewrite this chemical reaction. I'm not going to put in the symbols for the phase. It's just going to take too long. I guess I just did it once. And notice what I'm going to do is I'm just going to add it. So even though this is a negative sign, I'm going to add it to the right. The negative means you're losing. Adding it to the right means you're losing. For this next one, it's positive. So now I'm going to add it to the left. So I'm going to rewrite this reaction. And then I'm going to put it in at the very end. So if you notice, you don't have to do it this way, but it is pretty standard. If you're going to add the energy to the right, it's going to be the last thing on the right side. If you're going to add energy to the left side of the arrow, it's going to be the last thing on the left side of the arrow. So that's the standard way of doing it. So I'm just going to have you do the rest of these where you just add them to the right or the left side, depending on which reaction they are. And then for this one, I'll just do one. You're just doing the reverse. So basically, if you look at this reaction, it says, okay, the energy is on the left side of this arrow. So therefore, my delta H is going to be positive 182.6 kilojoules. And then if I had to rewrite this reaction with this term out of it, it would just look like this. N2 gas plus O2 gas. And then I would skip this whole section because now it's off to here. And it's going to look like 2NO2 gas. And it'll just be that. So all you're doing for these bottom four is you're just rewriting the reaction without the energy term in it. So it's literally just going to disappear. And instead, you're going to put it off to the side as a positive or negative. You're doing the reverse of what you did here. So again, I will send out an answer key so you can check your work to make sure you're doing this right. There will be a CASA learning on this online as well.